Hello, friend. Welcome back. Or if this is your first time here, welcome home. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's something else, something older. Tonight we're going to drift quietly into the largest things human eyes have ever seen. Not to conquer them, not to own them. Just to feel what it's like when size stops making sense and all that's left is wonder. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. No pressure, just an invitation. Now, let's drift. There's a feeling you get when you first try to imagine the size of the universe. It's not quite awe. It's not quite fear. It's closer to vertigo. The kind you feel when standing at the edge of something so vast that your body forgets how to measure distance. Your brain reaches for comparisons, a football field, a city, the ocean. And then those comparisons collapse. Because what do you compare infinity to? We've been trying to answer that question for thousands of years, and every time we think we've found the edge, the universe whispers, keep looking, there's more. Tonight we'll walk through 9 layers of largeness, from the moon, which felt impossibly far to our ancestors, to the edge of everything we can see. Each step will take us deeper into a kind of silence that numbers can't capture, because at some point, size stops being about measurement. It becomes about feeling. About realizing how small we are, and somehow, how connected. You don't need to understand everything. Just rest and let curiosity do the listening. Let's start with something familiar, something you've seen 1,000 times glowing softly in the night sky. The moon. It hangs there close enough to see with your naked eye, far enough to feel like a different world. And for most of human history, that's exactly what it was. A mystery. A light in the dark that no one could touch. But some minds refused to accept mystery as an answer. They wanted to know. How far? How big? What would it take to reach it? Around 240 BCE, a Greek mathematician named Eratosthenes stood in the city of Alexandria and did something extraordinary. He measured the Earth, not by walking it, not by guessing, by watching shadows. He heard that in the city of Syene, about 800 kilometers south, the sun shone directly down a well at noon during the summer solstice. No shadow, just light straight down. But in Alexandria, at that same moment, a stick cast a shadow, a small one, just a sliver of darkness against the ground. Eratosthenes knew what that meant. The earth wasn't flat, it was curved. And if he could measure the angle of that shadow, he could calculate the curve. He did. The angle was about 7 degrees, 1/50th of a full circle. So he multiplied the distance between the two cities by 50. And there it was, the circumference of the Earth, roughly 40,000 kilometers. He was off by less than 2%, with just a stick, a shadow, and geometry. Think about that for a moment. No satellites, no lasers, no machines, just observation and thought. That's the kind of mind that changes how we see everything. But Eratosthenes didn't stop there. Once you know the size of the Earth, you can start measuring other things, like the moon. A century earlier, another Greek thinker named Aristarchus had already tried. He watched a lunar eclipse the moment when the Earth's shadow falls across the moon's face. He noticed something. The shadow was curved, and it was big, about 2.5 times the width of the moon itself. If the Earth's shadow at the moon's distance was the large, and he knew the size of the Earth, he could work backward. He could estimate how far away the moon must be for the shadow to look that way. His answer: about 60 Earth radii, roughly 384,000 kilometers. He was almost exactly right. Imagine being Aristarchus, living in a time when most people believed the moon was a god or a lantern hung by the heavens. And you, with nothing but logic and patience, prove that it's a place, a real measurable place, not unreachable, just far. That's when far started to mean something different. It wasn't a wall anymore, it was an invitation. But here's the thing about that number: 384,400 kilometers. It's accurate. We know that now because we've sent spacecraft there. We've walked on it, we've left footprints that will last millions of years because there's no wind to erase them. But does the number help you feel the distance? Probably not. Because our brains didn't evolve to comprehend that scale. We understand the distance between our hand and a cup of water, between our home and the grocery store. But 384,000 kilometers. That's abstract. It's just math. So let's try something else. Let's make it smaller. If the Earth were the size of a basketball, the moon would be a tennis ball floating about 7 meters away. Close enough to see clearly. Far enough that you'd need to walk across a room to touch it. That feels real, doesn't it? That feels possible. But even that comparison hides something. The space between the Earth and the moon isn't empty. It's filled with silence, with radiation, with the faint hiss of solar wind. It's a place where temperature swings from 127 degrees Celsius in the sunlight to minus 173 in the shadow, where there's no air, no sound, no softness. Just rock and light and the slow pull of gravity holding two worlds in a dance that's lasted 4.5 billion years. When the Apollo astronauts made that journey in 1969, it took them 3 days. 3 days to cross a gap that ancient humans could only dream about. They described the Earth from that distance as a small, fragile blue marble floating in an ocean of black. The moon up close wasn't the glowing pearl it seemed from Earth. It was gray, dusty, covered in craters, each one a scar from a billion-year-old collision. Beautiful, yes, but in a quiet, lonely way. And here's something they noticed. From the moon, the Earth doesn't rise or set. It just hangs there unmoving because the moon is tidally locked. The same face always points toward us. So, if you stood on the lunar surface, the Earth would stay in roughly the same spot in the sky, slowly rotating, showing you different continents, different weather, different moments of day and night. A living clock, a reminder that home is still there, just out of reach. That distance, 384,400 kilometers, taught us something important. It taught us that impossible is often just not yet. For thousands of years, the moon was untouchable, a light we could only wonder about. And then, in a single generation, it became a place we could visit. Not because the distance changed, but because we did. But it also taught us something quieter, something we didn't expect. That distance changes perspective. From Earth, the moon is a companion, a nightlight, a thing we barely think about. But from the moon, the Earth becomes precious, rare. A blue glow in a dark sky holding everything we've ever known. Every person who's ever lived, every story, every war, every kiss, every quiet moment. All of it on that fragile little sphere. The astronaut Michael Collins, who orbited the moon alone while Neil Armstrong and Buzz Aldrin walked its surface, said something that still echoes. He said he didn't feel lonely. He felt awareness of how small we are and how much we carry. That's what distance does. It doesn't just separate, it reveals. So when we talk about the largest things in the cosmos, we're not really talking about size. We're talking about what happens when size forces us to see differently, to think differently, to feel differently. The moon isn't large, not compared to what's coming, but it was the first step. The first time we measured something beyond our world and realized we could reach it, that we could touch the untouchable. And once you take that first step, once you prove the distance is just a challenge, not a barrier, you start to wonder, what else is out there? What else can we measure? What else can we reach? The moon was humanity's first mirror. It showed us that we're capable of more than we think, that the universe isn't closed to us, that the night sky isn't a painting, it's a place, a real, measurable, reachable place. And all it took was a few curious minds, some shadows, and the willingness to ask how far. So tonight, as we drift deeper into the cosmos, remember this. Every great journey starts with a single question. And the moon was ours. But the moon was just the beginning. Because once we knew how far it was, we had a ruler, a way to measure the next step. And the next step was much, much brighter. The sun rises every morning. It sets every evening. It's been doing this your entire life, your parents' lives, their parents' lives. For as long as humans have existed, the sun has been the one constant, the giver of light, the keeper of time. So familiar that we forget to ask the simplest question, how far away is it? For most of history, no one knew. The sun was close enough to warm your skin, bright enough to hurt your eyes if you stared too long. But distance, that was a mystery wrapped in brilliance. Some ancient cultures thought it was a chariot driven across the sky by gods. Others believed it was a hole in the heavens, letting divine light pour through. Beautiful ideas, poetic ideas, but not answers. And then, in the 1600s, a man named Johannes Kepler started asking uncomfortable questions. Kepler wasn't satisfied with mystery. He wanted numbers. He had already figured out that planets don't move in perfect circles around the sun. They move in ellipses, stretched ovals like the orbits we're breathing. He'd discovered laws that described how planets speed up when they're closer to the sun, slow down when they're farther away. Mathematical laws, predictable laws. But to make those laws truly useful, he needed one crucial piece of information: the actual distance between the Earth and the sun. He tried, he failed. The technology wasn't there yet, but he planted a seed. A question that future astronomers couldn't ignore. Fast forward to 1761. The world was about to witness something rare, something that wouldn't happen again for over a century. Venus, the morning star, was going to pass directly between the Earth and the sun, a tiny black dot sliding across the face of our star. Astronomers called it the transit of Venus, and they realized something extraordinary. If observers in different parts of the world measured the exact timing of this transit, they could use a method called parallax to calculate the distance to the sun. Parallax is simple in theory. Hold your thumb up in front of your face, close one eye, then switch eyes. Your thumb appears to jump right. That's parallax, the shift in position based on your perspective. Now, imagine doing that with Venus. Observers in places like Norway and Tahiti would see Venus cross the sun at slightly different angles at slightly different times. By comparing those differences and knowing the distance between the observation points on Earth, astronomers could triangulate the distance to the sun. It sounds straightforward. It wasn't. Expeditions were launched to the far corners of the Earth. Some observers faced brutal weather. Others were stranded by war. The British astronomer Jeremiah Horrocks had tried observing a transit back in 1639, but died young, his data incomplete. The French astronomer Guillaume Le Gentil traveled to India for the 1761 transit, but clouds blocked his view. He waited 8 years for the next one in 1769. Clouds again. He went home only to find his relatives had declared him dead and divided his estate. Astronomy sometimes demands everything, but others succeeded. Captain James Cook sailed to Tahiti. Scientists in Norway, South Africa, and Russia set up their instruments. They measured, they calculated, and when all the data was combined, they arrived at a number approximately 150 million kilometers. We now call this distance 1 astronomical unit, or AU. It became the ruler by which we measure the solar system, 150 million kilometers. Let's sit with that for a moment. Because unlike the moon, which you can kinda wrap your mind around, the sun's distance is something else entirely. If you could drive a car to the sun at highway speed, it would take you about 170 years. If you walked, it would take over 3,000 years. Generations would live and die before you arrived. That's not a distance you can touch. It's a distance you can only imagine. But here's where it gets strange. Light doesn't care about our human sense of time. Light moves at 299,792 kilometers per second. At that speed, it takes about 8 minutes and 20 seconds for sunlight to reach Earth, which means every sunrise you've ever seen, every sunset you've ever watched is already in the past. The sun you're looking at existed 8 minutes ago. You're seeing a memory, a ghost of light traveling through the void. And if the sun suddenly vanished right now this instant, you wouldn't know for 8 minutes. The sky would still be bright, birds would still sing, the world would still turn. And then without warning, darkness. Not because the sun disappeared in that moment, but because the last light finally ran out. This is what distance in space really means. It's not just separation, it's time delay. The farther you look, the farther back you see. The universe is a gallery of memories frozen in light. Scientists suggest this concept changed everything. Once astronomers knew the distance to the sun, they could calculate the distances to other planets. They could map the solar system. They could predict eclipses, transits, orbital periods. The astronomical unit became the foundation. 1 astronomical unit, the length of our cosmic yardstick. But even with this knowledge, the sun remained humbling, because 150 million kilometers is just the distance. The sun itself, it's enormous. You could fit 1.3 million Earths inside it. If the Earth were a peppercorn, the sun would be a beach ball. And yet, from here it looks like a coin in the sky, small enough to block with your thumb. That's perspective, that's scale. Let's go back to Kepler for a moment. He never lived to see the transit of Venus measurements. He died in 1630, decades before the answer came. But his laws, his questions, his refusal to accept "we don't know" as a final answer, those things outlived him. He believed the universe was governed by harmony, by mathematical beauty. And he was right. The planets don't move randomly. They follow rhythms, patterns, laws that can be written down, tested, proven. But Kepler also believed something else. He thought the distances between planets corresponded to musical notes, that the solar system was a kind of cosmic symphony. He was wrong about that part. But maybe he wasn't entirely wrong about the spirit of it. Because when you learn that the Earth orbits the sun at 30 kilometers per second, that we're hurtling through space faster than any bullet, faster than sound, and yet we don't feel, it can't hear, it can barely comprehend it. There is something musical about that, a rhythm too vast for our ears, a song sung in silence. Here's a thought that might keep you awake or maybe help you drift. The sun has been shining for 4.6 billion years. Every photon of light that touches your skin began its journey at the core of the sun, where hydrogen atoms fuse into helium at 15 million degrees Celsius. That light doesn't go straight out. It bounces, scatters, ricochets through the sun's dense layers for thousands of years before finally breaking free. And then it races across 150 million kilometers in just 8 minutes to reach you, to warm your face, to make the grass green, to power every living thing on this planet. You are touching ancient light, light that's older than human civilization, older than the pyramids, older than writing. Every time you step into the sunshine, you're bathing in the exhaust of a star that's been burning since before the dinosaurs walked the earth. The sun doesn't just give us light, it teaches us humility. It shows us that we live in a narrow, fragile zone. Too close, and we'd burn. Too far, and we'd freeze. Earth sits in what scientists call the habitable zone, the Goldilocks region, where water can be liquid, where life can flourish. Move us just 5% closer or farther, and everything changes. We are here not by accident, but by an extraordinary alignment of distance, chemistry, and time. And yet, for all its importance, the sun is just one star. An average star. Not the biggest, not the brightest, not even particularly special. If you could see the Milky Way from the outside, the sun would be invisible, a grain of sand on a beach of 400 billion stars. But to us, to Earth, to every living thing that's ever opened its eyes to the sky, the sun is everything. It is the center, the anchor, the reason we exist. That's the paradox of cosmic scale. The farther out we measure, the smaller we become, but also somehow the more connected. Because that light, that ancient light, doesn't just fall on you, it falls on everyone. Every person who's ever lived has been warmed by the same star. We share that. Across time, across distance, across all the things that divide us. The sun taught us something else too. It taught us patience. It took thousands of years, countless failed attempts, and the combined effort of astronomers across continents to measure its distance. No single person did it alone. Kepler asked the question. Horrocks refined the method. Legendre suffered for it. Cook sailed to the edge of the known world for it. And together across generations, they found the answer. That's how we measure the universe. Not alone, not quickly, but together, slowly, carefully, one question at a time. So, when you see the sun tomorrow morning, let it linger in your mind a little longer. 150 million kilometers away, 8 minutes of light speed travel, a star that's been burning for billions of years will keep burning for billions more. Close enough to feel, far enough to remind you that closeness is relative, that even the things we take for granted, the things we see every single day, are miracles of distance and time. The sun was our first cosmic anchor, the first thing beyond Earth that we truly measured, and once we knew how far it was, once we had that astronomical unit in hand, we could start reaching farther, toward the edge of our solar system, toward places where sunlight grows cold, where distances stretch beyond comprehension, and where the silence deepens into something we're only beginning to understand. There's a place where the sun's voice fades, where its light still reaches but barely, where the warmth we take for granted becomes a memory, and the cold settles in like a truth we weren't ready to hear. It's the edge of our solar system, and it's farther than most of us can imagine. When we talk about the solar system, we often think of the planets: Mercury, Venus, Earth, Mars, the rocky ones close and warm. Then the giants Jupiter, Saturn, Uranus, Neptune, massive worlds of gas and ice spinning in the outer dark. But the solar system doesn't end at Neptune. It keeps going and going, until finally somewhere out there the sun's influence meets the galaxies and a line is drawn. Not a wall, just a whisper of separation. This is the frontier, the place where human-made objects have traveled farther than anything else in history. And what they found there wasn't emptiness, it was transition, a slow, quiet goodbye. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2. Their mission was to visit the outer planets, to send back images of worlds no human had ever seen up close. Jupiter's swirling storms, Saturn's delicate rings, Uranus tilted on its side, Neptune's violent blue winds. They did all of that. And then they kept going. Because their trajectory wasn't just about visiting planets. It was about leaving, about crossing a boundary no one had crossed before. The boundary is called the heliopause. It's the edge of the heliosphere, a bubble of charged particles constantly streaming out from the sun, known as the solar wind. Inside this bubble, the sun's magnetic field dominates. Outside interstellar space begins. The heliopause isn't a sharp line. It's more like a shoreline where 2 oceans meet, one of sunlight, one of starlight. Voyager 1 crossed it in August 2012, about 18 billion kilometers from Earth. That's roughly 121 astronomical units. To put that in perspective, if the distance from Earth to the Sun were the length of a football field, Voyager 1 would be over 2 kilometers away. Voyager 2 followed in November 2018, crossing at a slightly different point, revealing that the heliopause isn't uniform. It ripples, it breathes. But here's the astonishing part. Even at that distance, even after crossing into interstellar space, the Voyagers are still technically within the solar system. Because beyond the heliopause lies the Oort cloud, a vast shell of icy objects, dormant comets waiting in the dark. The Oort cloud is thought to extend outward for nearly 2 light years. That's about 125,000 astronomical units. Voyager 1, traveling at over 61,000 kilometers per hour, won't reach the inner edge of the Oort cloud for another 300 years, and it won't exit the outer edge for 30,000 years. Let that settle in. A spacecraft moving faster than anything humanity has ever built, and it will take 30,000 years to leave our solar neighborhood. That's how large our cosmic backyard really is. When the Voyager missions launched, their primary goal was exploration. But their creators knew something else. They knew these spacecraft would outlive us. So they included a message, a golden record etched with sounds and images from Earth, music from different cultures, greetings in 55 languages, the sound of a mother's heartbeat, a baby crying, waves on a shore. They encoded diagrams showing where Earth is located relative to nearby pulsars, a map in case someone finds it. Not in our lifetime. Maybe not in our species' lifetime, but someday. Carl Sagan, who helped design the record, called it a message in a bottle cast into the cosmic ocean. He knew the odds of it being found were almost zero, but he also knew that the act of sending it mattered. It was humanity saying we were here. We looked up. We tried to reach beyond ourselves. The Voyagers are still sending data back to Earth, faint signals traveling at the speed of light, taking over 22 hours one way to arrive. The spacecraft are so far away now that their transmitters powered by decaying plutonium send back just 160 bits per second. For comparison, a typical home internet connection is millions of bits per second. And yet scientists listen, they decode, they learn. What Voyager 1 discovered at the heliopause was unexpected. The solar wind didn't just stop, it piled up, like water hitting a dam. The pressure from interstellar space pushed back, creating a turbulent zone where particles collided, where magnetic fields twisted and snapped. It wasn't quiet, it was chaotic, a storm at the edge of calm. And the instruments detected something else, a hum, a faint vibration in the plasma, the electrically charged gas that fills the space between stars. Scientists suggest this hum might be the sound of interstellar space itself, a low-frequency drone caused by distant shock waves from exploding stars, from colliding gas clouds from the slow churn of the galaxy. It's not a sound you could hear with your ears. Space is a vacuum. But if you could translate those vibrations into audio, it would sound like a deep, resonant tone, the universe humming to itself. Now, let's talk about Pluto. For decades, Pluto was the 9th planet, the little world at the edge, small and cold and mysterious. In 2006, astronomers reclassified it as a dwarf planet, which upset a lot of people who grew up memorizing 9 planets instead of 8. But Pluto doesn't care what we call it. It's still out there orbiting the sun every 248 years, at an average distance of 5.9 billion kilometers. That's about 39.5 astronomical units. When New Horizons flew past Pluto in 2015, it sent back images that stunned everyone. Pluto wasn't a dead, cratered rock. It had mountains made of water ice as hard as steel at those temperatures. It had glaciers of frozen nitrogen flowing across its surface. It had a heart-shaped region now called Tombaugh Regio, named after Clyde Tombaugh, the man who discovered Pluto in 1930. And it had a thin atmosphere slowly escaping into space because Pluto's gravity is too weak to hold it. But what struck people most was the loneliness. Pluto is so far from the sun that sunlight there is 1,600 times dimmer than on Earth. If you stood on Pluto's surface, the sun would look like a bright star, not a disk. Noon would feel like deep twilight. And the cold is almost unimaginable. Minus 229 degrees Celsius, cold enough that the air itself would freeze. And yet, Pluto isn't alone. It has 5 moons. The largest Charon is so big relative to Pluto that the two orbit a common center of gravity between them. They're locked in a dance, each always showing the same face to the other, a cosmic partnership frozen in time. Beyond Pluto, The Kuiper Belt stretches outward, filled with thousands of icy bodies, remnants from the solar system's formation 4.6 billion years ago. Objects like Erisomia Makemake, worlds we're only beginning to understand. And beyond the Kuiper Belt, the scattered disk. And beyond that, the Oort cloud. Layer after layer of cold, dark, patient objects waiting. Here's a question. What does it mean to reach the edge? Because the more we explore, the more we realize there is no clean boundary. The solar system doesn't end. It fades. The sun's gravity still pulls on Oort cloud objects 2 light-years away. The sun's light still reaches them, faint but real. And yet, out there, the galaxy's gravity is stronger. The interstellar wind is louder. The balance shifts. This is where we learn that space isn't empty. It's full of particles, fields, forces we can barely detect. The Voyagers taught us that. They crossed a line we thought was simple and found complexity, layers, transitions. The universe doesn't give us sharp answers. It gives us gradients. There's a thought experiment scientists sometimes consider. If you could stand at the heliopause looking back toward the sun, what would you see? The sun would be the brightest star in the sky, but still just a star. You couldn't make out the planets. You couldn't see Earth. Everything you've ever known, every person, every place, every moment would be invisible, compressed into a single point of light. And if you turned around facing outward, you'd see the Milky Way, a river of stars stretching across the sky. You'd be standing at the threshold, not inside, not outside, just between. That's what the edge of the solar system really is. A threshold, a place of transition. And it reminds us that belonging isn't about boundaries, it's about connection. The sun's light reaches Pluto. Voyager's signal reaches Earth. We are still connected even across billions of kilometers, even across decades of travel time. The Voyager spacecraft will eventually run out of power. Probably sometime in the mid-2000s, their instruments will shut down one by one. Their transmitters will go silent, and they'll drift inert through the galaxy. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. It won't stop. It won't slow down. It will just drift by, a silent ambassador from a world that may no longer exist. But even in silence, they'll carry something. That golden record, those sounds, those images. A reminder that once on a small blue world orbiting an average star, a species looked up and wondered, and built, and sent a message knowing it might never be answered. That's not futility, that's hope. Quiet, patient, enduring hope. The edge of the solar system isn't an ending, it's a beginning. Because once you cross it, once you step beyond the sun's embrace, you're in the space between stars. And that's where the real distances begin. Distances so vast that even light, the fastest thing in the universe, takes years to cross them. And the nearest star, the one we'll drift toward now, is waiting in that darkness just over 4 light-years away. 4.24 light-years. That's the distance to the nearest star beyond our sun. It doesn't sound like much, does it? Just 4 years of light travel. We measure human lifespans in decades. 4 years feels manageable, reachable even. But light moves at 299,792 kilometers per second. And 4 years of that speed equals about 40 trillion kilometers. 40 million, a number so large it stops meaning anything until you try to cross it. Proxima Centauri, a small red star barely visible even with a telescope. Not bright, not impressive, but closer to us than any other star in the galaxy. And yet, impossibly unreachably far. The star belongs to a system called Alpha Centauri, a trio of stars bound by gravity orbiting each other in a slow cosmic dance. Alpha Centauri, A and B, are the brighter pair, similar to our sun, locked in an eternal waltz. Proxima is the third companion, smaller, dimmer, orbiting the pair at a distance so vast it takes 500,000 years to complete one orbit. Proxima is a red dwarf about 1/8 the mass of our Sun, glowing faintly in the infrared. If you replaced our Sun with Proxima Centauri, Earth would freeze. The star simply doesn't produce enough heat. But it does have planets, at least 2 that we know of. One of them, Proxima Centauri b, orbits in the star's habitable zone, where liquid water could theoretically exist. A world about 1.3 times the mass of Earth, circling its dim star every 11 days. Imagine that for a moment. A planet, possibly rocky, possibly with an atmosphere, orbiting the nearest star to our own. And we can't reach it. Not yet. Maybe not ever. Here's why. If we sent the fastest spacecraft humanity has ever built, the Parker Solar Probe, which reaches speeds of about 700,000 kilometers per hour as it dives toward the Sun, it would still take over 6,300 years to reach Proxima Centauri. That's longer than recorded human history. The pyramids of Egypt are only 4,500 years old. The spacecraft would arrive at Proxima long after the civilization that launched it had risen, fallen, and been forgotten. And that's assuming it was aimed in the right direction, which it isn't. The Parker Solar Probe is studying the Sun not leaving the solar system. Voyager 1, which is leaving, is traveling at about 61,000 kilometers per hour. At that speed, it would take over 73,000 years to reach Proxima. 73,000 years. Longer than modern humans have existed as a species. This is the gulf between stars, not empty space, not silence, but time. Unimaginable stretches of time where distance and duration become the same thing. For most of human history, we didn't even know other stars were suns. We thought they were holes in the sky, or distant fires, or the souls of the dead watching over us. Beautiful ideas, comforting even, but not true. It wasn't until 1838 that a German astronomer named Friedrich Wilhelm Bessel proved mathematically that stars were distant suns. He did it using parallax, the same method used to measure the sun's distance. But this time, instead of observing Venus crossing the sun, he observed a star called 61 Cygni from opposite sides of Earth's orbit 6 months apart. The star appeared to shift ever so slightly against the background of more distant stars. From that tiny shift, less than 1 arc second, Bessel calculated the star's distance about 11 light years. It was the first time a human being measured the distance to another star. And the number was staggering, far beyond anything people had imagined. The universe wasn't just large, it was incomprehensibly vast. Bessel didn't measure Proxima Centauri. That star wasn't discovered until 1915 by the Scottish astronomer Robert Innes, working at an observatory in South Africa. Innes noticed a faint red star with a large proper motion, meaning it was moving noticeably across the sky relative to other stars. He calculated its distance using parallax and realized it was closer than any star yet discovered, just over 4 light years away. The closest neighbor we have. But even knowing it's there doesn't mean we can visit. The challenge isn't just distance, it's energy. To accelerate a spacecraft to even a fraction of the speed of light requires energy we don't currently have. Chemical rockets like the ones that took us to the moon are far too slow. Ion drives, which use electricity to propel charged particles, are more efficient, but still take decades to build up meaningful speed. Nuclear propulsion has been proposed using controlled explosions to push a spacecraft forward, but the engineering challenges are immense. And even if we solve those problems, even if we could travel at 10%, the speed of light, the journey to Proxima would still take over 40 years. 40 years. That's a human lifetime. You'd need a crew willing to spend their entire lives in transit knowing they'd never return. Or you'd need generational ships where children are born, in space, raised in space, grow old in space, and their children continue the journey. Ships that are entire worlds unto themselves. Mobile civilizations. Some scientists suggest we don't need to send people. We could send robots. Tiny probes accelerated by powerful lasers on Earth, reaching speeds close to 20% the speed of light. The Breakthrough Starshot initiative, backed by physicist Stephen Hawking before his death, proposed exactly that. Lightweight spacecraft, each weighing just a few grams, propelled by laser sails. They could reach Proxima in about 20 years, and then another 4 years for their signals to return to Earth. A 24-year round trip for information, not for humans, just data, images, measurements. But even that faces problems. A laser powerful enough to accelerate these probes would need to be enormous, consuming vast amounts of energy. The probes would be so small and light that even a collision with a single dust grain at those speeds could destroy them. And once they arrived, they'd fly past Proxima in a matter of hours, unable to slow down, unable to stop. Snapshots, not exploration. This is the reality of interstellar travel. It's not impossible. It's just hard. Harder than anything humanity has ever attempted. Harder than splitting the atom, landing on the moon, or sequencing the human genome. Because the distances between stars aren't just measurements. They're barriers built from the fabric of space-time itself. And yet, we keep thinking about it. We keep imagining. Because Proxima Centauri represents something more than a star. It represents the idea that we're not alone in the universe. That there are other worlds, other skies, other sunrises. Proxima b, that small planet in the habitable zone, might have water. It might have an atmosphere. It might have life. We don't know. We can't know not from here. But the possibility pulls at us. There's a thought experiment that astronomer Carl Sagan used to pose. He called it the pale blue dot. In 1990, as Voyager 1 was leaving the solar system, Sagan convinced NASA to turn the spacecraft's camera around and take one last photograph of Earth from 6 billion kilometers away. In that image, Earth appears as a tiny speck, less than a pixel suspended in a beam of scattered sunlight. Sagan wrote about that image. He said, "Look again at that dot. That's here, that's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard, of every human being who ever was lived out their lives." Now imagine Proxima Centauri has a planet with life. Imagine someone there looking back at our sun, seeing it as a pale yellow dot in their sky. They'd have no idea we exist. No idea that on this tiny blue world orbiting that unremarkable star, there's a species building machines, asking questions, dreaming of crossing the void between their star and ours. And we'd have no idea about them. This is the loneliness of distance. We're separated not by choice, but by physics. By the speed of light, which is both the fastest thing in the universe and still far too slow for the distances we want to cross. But here's the strange comfort in that. Light from Proxima Centauri, the light you'd see if you looked at it through a telescope tonight, left that star 4.24 years ago. It's been traveling through the void undisturbed for over 4 years. And tonight, it reaches your eye. You're seeing the past. A photon that began its journey before you started reading this sentence, before you woke up this morning, before the last election, before the pandemic. It traveled across 40 trillion kilometers, through empty space, through interstellar dust, through the outer reaches of our solar system, through Earth's atmosphere, and into your eye. That's a kind of connection. Not physical, not immediate, but real. We are touched by starlight. Constantly. Every star you see in the night sky is reaching across impossible distances to meet you. And you, by looking up, are completing that journey. Scientists have proposed something called the cosmic speed limit. It's the speed of light, and according to Einstein's theory of relativity, nothing with mass can reach it. The faster you go, the more energy you need. And as you approach light speed, the energy required approaches infinity. It's a wall built into the universe, not to keep us trapped, but to remind us that some things take time. That distance has meaning. That the universe isn't meant to be rushed. Maybe that's okay. Maybe the fact that Proxima Centauri is 4 light years away isn't a tragedy. Maybe it's a reminder that exploration takes patience, that discovery takes generations, that the questions we ask aren't always meant for us to answer. Sometimes we ask them so that our children or their children or someone centuries from now can find the answers. And that's enough. Because the nearest star, that faint red glow 40 trillion kilometers away, isn't just a destination. It's a mirror. It shows us how far we've come and how far we still have to go. It shows us that curiosity doesn't die just because something is hard. It grows. It persists. It reaches even when reaching seems impossible. Proxima Centauri is still there, glowing quietly, orbited by at least one world that might in some distant future be visited by something we built. Not by us, but by the part of us that refuses to stop wondering. And that's a kind of immortality, not of the body, but of the question. The space between stars isn't empty. It's full of light moving slowly, carrying stories from distant suns. And now, we turn from the nearest star to something even larger. Not a single sun, but a river of them. 400 billion lights swirling in a spiral. Our galaxy. Our home. Vast enough that even traveling at light speed, it would take 100,000 years to cross. You are here, right now, reading these words, breathing, existing. But where is here, really? You might say your city, your country, Earth. But zoom out a little more. Keep going. Past the moon, past the sun, past the outer planets and the Oort cloud. Keep drifting until the solar system becomes a speck, and then nothing. And you'll find yourself inside something much larger. A spiral of light 100,000 light years across, containing somewhere between 200 and 400 billion stars. Our galaxy. The Milky Way. And here's the strange part. You're not standing still. You're moving through it at 828,000 kilometers per hour. Faster than a bullet. Faster than sound. Faster than anything you've experienced on Earth. And you don't feel a thing. For most of human history, we didn't know the Milky Way was a galaxy. We saw it as a band of light stretched across the night sky, glowing softly like spilled milk. That's where the name comes from. The Greeks called it Galaxies Kyklos, the Milky Circle. The Romans called it Via Lactea, the Road of Milk. Ancient cultures had their own stories. Some saw it as a river, others a path for souls traveling to the afterlife. No one imagined it was made of stars. Billions of them so distant they blurred together into a faint glow. It wasn't until 1610 that Galileo Galilei pointed his telescope at the Milky Way and saw the truth. Not a cloud, not a mist, but stars. Countless stars packed so densely they merged into light. He wrote in his journal that the Milky Way was nothing but a congeries of innumerable stars, a crowd, a gathering. And for the first time, humans began to understand. The universe was larger than anyone had dreamed, but even Galileo didn't know how large. He thought the Milky Way was the entire universe. That beyond it, there was nothing. It would take another 300 years for us to learn the truth. In 1918, an American astronomer named Harlow Shapley made a discovery that changed everything. He was studying globular clusters, dense spheres of ancient stars that orbit the galaxy like moons around a planet. Shapley noticed something strange. These clusters weren't evenly distributed across the sky. Most of them were concentrated in one direction, toward the constellation Sagittarius. He realized what that meant. The globular clusters were orbiting the center of the galaxy. And if most of them were in one direction, that meant the center of the galaxy was in that direction too, which meant we weren't at the center. We were somewhere out in the suburbs, far from the core. Shapley calculated the distance. About 26,000 light years from the galactic center. Not at the heart of things, not special. Just one more star among hundreds of billions drifting through space at incomprehensible speeds. This was a blow to human ego. For thousands of years, we believed that we were at the center of everything. First, we thought Earth was the center of the universe. Then Copernicus showed us we orbit the sun. Then Shapley showed us the sun isn't even at the center of the galaxy. We've been demoted over and over from the center of creation to a quiet corner of a spiral arm called Orion Cygnus, orbiting a galaxy we can barely comprehend. But maybe that's not a demotion. Maybe it's a liberation. Because if we're not the center, if we're just one small part of a vast interconnected whole, then we're free. Free to explore, free to wonder, free to be small. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped structure of stars, with spiral arms curving outward like water swirling down a drain. Our solar system sits about halfway out along one of those arms, moving through space at 828,000 kilometers per hour relative to the galactic center. But we're not moving in a straight line. We're orbiting. The entire solar system's sun and all makes one complete lap around the galaxy every 230 million years. Astronomers call this a galactic year. In the time it took for dinosaurs to rise, dominate the Earth, and go extinct, the solar system completed less than one full orbit. We have only gone around the galaxy about 20 times since the sun was born 4.6 billion years ago. Think about that. The last time we were in this exact spot in the galaxy, the Earth was a molten ball of rock. There was no life, no oceans, no atmosphere. And the next time we come around 230 million years from now, who knows what will exist? Maybe humans will still be here. Maybe we'll be gone. Maybe something else will have risen, looked up at the stars, and wondered the same things we wonder now. But the galaxy doesn't care. It keeps turning. Slowly, patiently, indifferent to the small dramas of the creatures living within it. Now let's talk about what the Milky Way actually is. Not just a collection of stars, but a structure, a living, evolving system. At its core sits a supermassive black hole called Sagittarius, a star pronounced Sagittarius A star. It has a mass of about 4 million suns compressed into a region smaller than the orbit of Mercury. We can't see it directly because black holes don't emit light, but we can see the stars around it whipping through space at incredible speeds, pulled by gravity so strong it bends space-time itself. In 2020, Andrea Ghez and Reinhard Genzel won the Nobel Prize in Physics for tracking these stars and proving the black hole's existence. One star, called S2, completes an orbit around Sagittarius, A star every 16 years, reaching speeds of 7,600 kilometers per second, nearly 3% the speed of light. That's how strong gravity is near the center of our galaxy. The black hole isn't eating everything. It's just sitting there, a gravitational anchor holding the galaxy together. Most of the stars in the Milky Way will never get close enough to be pulled in. They orbit at safe distances, like planets around a sun. But every so often, a star wanders too close. And when that happens, the black hole's gravity tears it apart, stretching it into long strands of superheated gas. Astronomers call this spaghettification. Not a comforting name, but accurate. Beyond the core, the galaxy spreads out in layers. The galactic bulge, a thick concentration of old stars glowing yellow and red. The disk where most of the star formation happens, where new suns are being born from clouds of gas and dust. The spiral arms bright with young blue stars, massive and short-lived, burning hot and dying fast. And surrounding all of it, the halo, a sparse sphere of ancient stars and dark matter, the invisible substance that makes up most of the galaxy's mass. Dark matter. We can't see it, can't touch it, can't detect it directly. But we know it's there because the galaxy's rotation doesn't make sense without it. Stars at the edge of the galaxy orbit just as fast as stars near the center, which shouldn't be possible based on the visible mass alone. There's not enough gravity to hold them in place, unless there's something else, something we can't see. Scientists suggest dark matter is a form of mass that doesn't interact with light, only with gravity. It forms a vast invisible web, holding galaxies together, shaping the structure of the universe. And we still don't know what it is, one of the great mysteries of modern science, hidden in plain sight. Here's something that might keep you awake or help you drift. The Milky Way isn't alone. It's part of a cluster of galaxies called the Local Group, about 54 galaxies bound together by gravity. Most of them are small dwarf galaxies orbiting the two largest ones, the Milky Way and Andromeda. And Andromeda is moving toward us, not slowly, not gently, but fast, at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide. But collide isn't quite the right word. Galaxies are mostly empty space. The distances between stars are so vast that when two galaxies merge, very few stars actually hit each other. Instead, they pass through like two clouds drifting together. What does collide are the gas clouds, the dust, the raw material for new stars. And when that happens, star formation explodes. New suns ignite by the millions. The night sky, if anyone's around to see it, will be filled with brilliant short-lived stars, burning bright and dying fast. The Milky Way and Andromeda will spiral around each other, pulled by gravity, merging over hundreds of millions of years. Eventually, they'll settle into a new shape, not a spiral anymore. An elliptical galaxy, a smooth blob of stars, slowly aging, slowly fading. Astronomers have already given it a name, Milkomeda, a blending of two worlds, two histories, two collections of stars, dust, and dreams. But by then, the sun will be dying too. In about 5 billion years, it will swell into a red giant engulfing Mercury and Venus, scorching the Earth. Life, if it still exists, will have moved elsewhere, or adapted, or ended. The galaxy won't notice. It will keep spinning, keep evolving indifferent to the small blue world that once looked up and wondered. There's a question that people sometimes ask. If we're moving so fast, why don't we feel it 828,000 kilometers per hour? Sounds like it should tear us apart. But motion isn't what you feel. Acceleration is. Change in motion. And the galaxy's rotation is so smooth, so constant, that there's no jolt, no shift, no sensation. It's like being in a car on a perfectly straight highway. If you close your eyes, you can't tell you're moving. The galaxy is that highway, smooth, steady, eternal. But every so often the ride gets bumpy. The Milky Way has collided with other galaxies before, smaller ones mostly. Dwarf galaxies that wandered too close and were torn apart by tidal forces their stars absorbed into the Milky Way's structure. Scientists have found evidence of these ancient collisions, streams of stars moving in strange directions, remnants of galaxies that no longer exist. The Milky Way isn't just a structure, it's a graveyard, a monument to everything it's consumed, and it's still growing, still pulling in new material, still reshaping itself. Galaxies don't die, they transform. Let's come back to Earth for a moment. On a clear, dark night, far from city lights, you can see the Milky Way stretched across the sky. A pale band of light arcing from horizon to horizon. You're looking at the edge of the galactic disk, the combined glow of billions of stars too faint to see individually. You're looking at your home from the inside. And if you could step outside the galaxy, if you could float above it and look down, you'd see a spiral, a pinwheel of light. And somewhere in that spiral, lost in the glow, would be the sun. And orbiting that sun, a small blue world. And on that world, you, looking up, wondering. We are not separate from the galaxy. We are made of it. Every atom in your body was forged in the core of a star that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces scattered into space when those stars exploded and slowly gathered into new clouds, new stars, new planets. You are stardust, literally, not a metaphor, a fact. The galaxy didn't just create you, it is you. And when you die, when the Earth dies, when the sun dies, those atoms will return to the galaxy. They'll drift through space, join new clouds, form new stars, new worlds. The cycle continues. Nothing is lost. Everything is transformed. That's what the Milky Way teaches us. Not that we're small, but that we're connected, part of a story that's been unfolding for 13.6 billion years since the galaxy first formed from the debris of even older stars. We didn't appear out of nowhere. We emerged from the galaxy itself, shaped by its chemistry, its physics, its patient and different processes. And we'll return to it someday, not as individuals, but as elements, as the raw material for whatever comes next. There's a comfort in that, if you let it settle. You're not separate, you're not alone. You're part of something unimaginably vast, unimaginably old, and still unfolding. The Milky Way is your home, not just the planet, not just the solar system, the whole galaxy. Every star you see in the night sky is a neighbor. Some closer, some farther, but all connected by gravity, by light, by the shared history of cosmic evolution. And yet, the Milky Way is just one galaxy, one island in an ocean of islands. Beyond it there are others, billions of them, each one a universe unto itself. And the nearest large one, Andromeda, is drifting closer, slowly inevitably carrying its own billions of stars toward ours. There's a smudge in the night sky. If you know where to look, if the sky is dark enough, you can see it with your naked eye. A faint, fuzzy patch in the constellation Andromeda. For thousands of years, people thought it was a cloud, a nebula, something small and nearby. They had no idea they were looking at an entire galaxy, 2.5 million light-years away, containing over 1 trillion stars, moving toward us at 110 kilometers per second. Andromeda, our closest large galactic neighbor. And in 4.5 billion years, it will be here. For most of human history, we didn't know galaxies existed. The fuzzy patches in the sky, the ones that didn't move like planets or twinkle like stars, were called nebulae, from the Latin word for cloud. Astronomers cataloged them, gave them numbers, observed them through telescopes, but no one knew what they were. Some thought they were clouds of gas within the Milky Way, glowing from the heat of newborn stars. Others suspected they might be something else, something farther, but there was no way to prove it. Then came Edwin Hubble, not the telescope, the man. In 1924, working at the Mount Wilson Observatory in California, Hubble turned the 100-inch Hooker telescope toward the Andromeda Nebula, as it was called then. He was looking for Cepheid variables, a special type of star that pulses in brightness with a regular period. These stars are useful because their pulsation period is directly related to their intrinsic brightness. If you measure how fast a Cepheid pulses, you can calculate how bright it actually is. And if you compare that to how bright it appears from Earth, you can determine its distance. Hubble found Cepheids in Andromeda, and when he calculated their distance, the number was staggering. About 900,000 light-years. We now know the actual distance is closer to 5 million light-years, but even Hubble's first estimate was revolutionary, because it proved beyond doubt that Andromeda was not inside the Milky Way. It was outside, far outside, an entirely separate galaxy, an island universe as some astronomers called it. And if Andromeda was a separate galaxy, then so were the other spiral nebulae scattered across the sky. The universe overnight became incomprehensibly larger. Hubble's discovery shattered the old cosmology. The Milky Way wasn't the entire universe. It was just one galaxy among countless others, each one a vast collection of stars, gas dust, and mystery. And Andromeda, that faint smudge you can see on a dark night, was actually larger than the Milky Way, more massive, more luminous, a giant drifting through the void. But Andromeda isn't alone, neither is the Milky Way. The two galaxies are part of a cosmic neighborhood called the Local Group, a gravitationally bound cluster of about 54 galaxies. Most of them are small dwarf galaxies with poetic names like the Large Magellanic Cloud, the Small Magellanic Cloud, the Sculptor Dwarf, the Fornax Dwarf, little collections of stars orbiting the two giants like moons around planets. The Milky Way has at least 14 known satellite galaxies. Andromeda has even more, And together, this whole family drifts through space bound by gravity, isolated from other galaxy groups by millions of light years of nearly empty space. The local group spans about 10 million light years. To put that in perspective, if you shrunk the Milky Way down to the size of a dinner plate, Andromeda would be another dinner plate about 25 meters away. The dwarf galaxies would be coins and buttons scattered between them. And beyond the local group in every direction, other galaxy groups and clusters, each one separated by vast cosmic voids. Now, let's talk about what's happening between the Milky Way and Andromeda, because they're not just neighbors. They're on a collision course. Astronomers have measured Andromeda's motion using something called blue shift. Most distant galaxies are redshifted, meaning their light is stretched toward longer wavelengths as they move away from us due to the expansion of the universe. But Andromeda's light is blue shifted, compressed, which means it's moving toward us, fast. At 110 kilometers per second, Andromeda is closing the gap. In 4.5 billion years, the two galaxies will begin to merge. But calling it a collision gives the wrong impression. Galaxies are mostly empty space. The average distance between stars in a galaxy is about 5 light years. When the Milky Way and Andromeda pass through each other, very few stars will actually collide. It's more like two swarms of bees flying through each other, lots of near misses, very few direct hits. But even if stars don't collide, gravity does its work. The two galaxies will distort each other, pulling out long tidal tails of stars and gas. Spiral arms will stretch and break. Star formation will spike as gas clouds collide and compress, igniting waves of new stars. The night sky, if Earth is still around to see it, will be transformed. Instead of one faint band of the Milky Way, the sky will be filled with scattered clusters of stars, glowing nebulae, and eventually, the looming disk of Andromeda growing larger with each passing million years. Scientists have run simulations of this merger, supercomputers modeling the gravitational interactions of billions of stars. The results are beautiful and strange. The two galaxies approach each other, pass through, swing around due to gravity's pull, and come back for a second pass, then a third. Each time they lose energy to tidal friction, spiraling closer together. Eventually, after several billion years, they settle into a new configuration. Not a spiral anymore, an elliptical galaxy, a smooth, featureless blob of stars slowly rotating, slowly aging. Astronomers have already named it Milkomeda, a blend of the two names, a new galaxy born from the merger of two old ones. And it will be massive, somewhere around 5 trillion solar masses, one of the largest galaxies in the local universe. But here's the thing, by the time this happens, the sun will be gone, or rather transformed. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin fusing helium. It will swell into a red giant, expanding outward until it engulfs Mercury and Venus. Earth might survive, but barely. The oceans will boil away. The atmosphere will be stripped. Life, if it hasn't already left, the planet will end. And a billion years later, the sun will shed its outer layers, leaving behind a white dwarf, a dense core about the size of Earth, slowly cooling over trillions of years. So, the merger of the Milky Way and Andromeda will happen in a solar system that no longer looks like ours. The question is, will anyone be around to see it? Will humanity have survived long enough to witness two galaxies becoming one? Will we have left Earth colonized other stars spread across the galaxy? Or will we be gone? Our chapter in the story closed leaving the universe to continue without us. It's a humbling thought, that the cosmos operates on timescales so vast that even the most momentous events like the collision of galaxies happen long after we're gone. But it's also strangely comforting, because it means the universe doesn't need us. It will go on with or without us, creating new structures, new stars, new possibilities. Our existence, our civilizations, our art and science and dreams, all of it is a brief flicker in a story that's been unfolding for 13.8 billion years. and will continue for trillions more. Let's step back and think about the local group as a whole. Why does it exist? Why are these galaxies clustered together instead of scattered randomly through space? The answer is gravity and dark matter. Scientists suggest that the local group formed from slight variations in the density of matter in the early universe. Regions that were slightly denser than average pulled in more matter, which made them even denser, which pulled in even more matter. A feedback loop. Over billions of years, these overdense regions collapsed into galaxies and groups of galaxies and clusters of groups. The structure of the universe isn't random, it's hierarchical. Small clumps merge into larger clumps, which merge into even larger ones. But the local group is relatively isolated. The nearest large cluster is the Virgo cluster, about 65 million light-years away, containing over 1,500 galaxies. And beyond Virgo, other clusters: Coma, Hercules, Fornax. Each one a city of galaxies separated by vast cosmic deserts. There's a thought experiment that astronomers sometimes use to understand cosmic scales. Imagine the entire observable universe shrunk down, so that the Milky Way is the size of a grain of sand. At that scale, Andromeda would be another grain of sand about 2 millimeters away. The local group would fit on the tip of your finger. The Virgo cluster would be about 5 centimeters away. And the observable universe, the entire sphere of everything we can see, would stretch out to about 100 meters in every direction, filled with grains of sand, billions of them, each one a galaxy, each one containing hundreds of billions of stars. That's the scale we're dealing with. And the local group is just our neighborhood, our small corner of a much, much larger cosmos. But let's come back to Andromeda, because there's something beautiful about knowing it's there, about knowing that on a clear night when you look up, you can see the combined light of a trillion stars 2.5 million light-years away. The photons entering your eye began their journey before humans existed, before Homo sapiens walked the Earth, when our ancestors were still Homo erectus using stone tools, learning to control fire. The light you're seeing now left Andromeda when the world was colder, the ice sheets thicker, the continents arranged differently. And it's been traveling through the void ever since, undisturbed until this moment. Until you. That's a kind of time travel, not forward or backward, but across. You're seeing Andromeda as it was not as it is. And by the time the light from our galaxy reaches Andromeda, 2.5 million years will have passed here too. If there's anyone there looking back at us, they're seeing the Milky Way as it was before humans existed, before cities, before language, before civilization. Just stars, turning, glowing, indifferent. There's a loneliness in that, a sense of separation. We and Andromeda are neighbors, yes, but neighbors separated by such vast distances that communication, even at the speed of light, would take 5 million years round trip. By the time you sent a message and received a reply, entire species could rise and fall. Continents could drift. Stars could be born and die. That's not a conversation. That's an echo across deep time. And yet we're connected by gravity, by the shared history of cosmic evolution, by the fact that both galaxies formed from the same primordial hydrogen, the same quantum fluctuations in the early universe. Andromeda and the Milky Way are siblings in a sense, born from the same cosmic material, drifting toward each other, destined to merge. Some astronomers wonder what the merger will look like from the inside. If you could stand on a planet orbiting a star in the Milky Way when Andromeda arrives, what would you see? At first, nothing. The galaxies are too far apart. But over millions of years, Andromeda would grow in the sky. A faint smudge becoming a glowing oval, then a disk, then a massive spiral filling half the night. Stars from Andromeda would begin to appear scattered across the sky, no longer clustered in a distant patch, but mixed with our own stars. The night sky would become richer, brighter, more crowded, and eventually the two galaxies would be so intertwined that you couldn't tell which stars came from where. It would be a slow apocalypse, not violent, not sudden. Just a gradual merging of two worlds, two histories, two collections of stars and dust and chemistry. And from the ashes of that merger, something new. Milkomeda, a galaxy that never existed before, a future written in gravity and time. But that future is billions of years away. Right now, Andromeda is still out there drifting closer 1 second at a time. And the local group is still intact, still turning, still held together by invisible threads of gravity and dark matter floating in a universe that's expanding, cooling, growing ever more vast and empty. The local group teaches us something important. That proximity doesn't mean closeness, that neighbors can be millions of light years away and still be bound together, that the universe organizes itself into structures, hierarchies, families of galaxies, each one connected by forces we can measure but not always see. And soon, we'll zoom out even farther, beyond the local group, beyond isolated clusters, to the largest structures in the universe, the superclusters, the cosmic web, the architecture of everything, where galaxies aren't scattered randomly but woven into threads and filaments like neurons in a cosmic brain. A pattern so large it takes hundreds of millions of light years just to see its shape. Imagine looking at the universe from so far away that galaxies become dots, not individual stars. Not even individual galaxies, just dots, scattered across the darkness like grains of sand on black velvet. And then, as your eyes adjust, you notice something. The dots aren't random. They're arranged, connected, flowing along invisible threads, clustering at intersections, leaving vast, empty spaces in between. The universe has a structure, a pattern, an architecture so large it takes hundreds of millions of light years just to see its shape. This is the cosmic web, and we live inside it. For decades, astronomers thought galaxies were scattered randomly through space. Here and there, no pattern, no order, just chaos. But as telescope technology improved, as surveys mapped more and more galaxies, a different picture emerged. Galaxies weren't scattered randomly. They were clustered, grouped, organized into enormous structures called superclusters, separated by regions of almost nothing, cosmic voids, and connecting everything like the strands of a spider's web were filaments. Long, thin streams of galaxies stretching across hundreds of millions of light years. The discovery of this structure was gradual. In the 1980s, astronomers began mapping the positions of galaxies in 3 dimensions, measuring not just their location on the sky, but also their distance from Earth using redshift. And when they plotted those positions, they saw something astonishing. Galaxies formed walls, sheets, filaments, with enormous voids in between. One of the first major discoveries was the CFA2 Great Wall, a structure stretching over 500 million light years, containing tens of thousands of galaxies arranged in a thin sheet. It was the largest known structure in the universe at the time, and it shattered the assumption that the universe was homogeneous on large scales. But the Great Wall was just the beginning. As surveys expanded, astronomers found even larger structures. The Sloan Great Wall, the Hercules Corona Borealis, Great Wall, stretching over 10 billion light years so large, it challenges our understanding of how structures can form in a universe only 13.8 billion years old. And in 2014, researchers identified the supercluster we live in. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is our cosmic address, bigger than the local group, bigger than the Virgo cluster, a supercluster containing about 100,000 galaxies stretching across 520 million light years. And we're not at the center. We're on the outskirts in a relatively quiet region, drifting through space at about 630 kilometers per second, pulled by something called the Great Attractor. The Great Attractor is a gravitational anomaly, a region of space where the density of galaxies is higher than average, creating a gravitational pull so strong, it's dragging the Milky Way, Andromeda, the entire local group, and thousands of other galaxies toward it. We can't see the Great Attractor directly because it lies behind the Milky Way's galactic plane, obscured by dust and stars, but we can measure its effect. We can see galaxies moving toward it faster than they should be, based on visible mass alone. Scientists suggest there's a massive concentration of dark matter there, invisible but real, shaping the flow of galaxies like water circling a drain. And beyond the Great Attractor, there's something even larger, the Shapley supercluster, a massive concentration of galaxies about 650 million light-years away, containing over 8,000 galaxies. It's pulling on us too. And beyond that, more superclusters, more filaments, more structure layered upon structure, stretching to the edge of the observable universe. The cosmic web is held together by dark matter. We've mentioned dark matter before, but here at the largest scales, its role becomes undeniable. Galaxies don't have enough visible mass to create the gravitational pull needed to form these structures. There's not enough gas dust and stars to explain why galaxies cluster the way they do, unless there's something else, something we can't see. Dark matter forms the skeleton of the cosmic web, an invisible scaffolding upon which visible matter collects. Galaxies form along dark matter filaments like dew condensing on a spider's web. The filaments themselves are thought to be rivers of dark matter flowing through the universe, connecting clusters and superclusters in a vast interconnected network. Simulations of the early universe run on supercomputers show this process unfolding. Start with tiny fluctuations in density quantum ripples from the Big Bang and let gravity do its work over 13.8 billion years. The denser regions pull in more matter. The less dense regions empty out. Over time, matter flows along filaments, pools at intersections, and creates clusters. And in between, voids grow larger and emptier. The result looks remarkably like the universe we observe. Filaments, walls, voids, a cosmic web. But here's what's haunting about the voids. They're not completely empty. There are a few galaxies in there scattered and isolated, but mostly they're just space, dark, silent, expanding. One of the largest known voids is the Boötes void discovered in 1981. It's roughly 330 million light-years in diameter and contains only about 60 galaxies, far fewer than expected for a region that size. If the Milky Way were located in the Boötes void, our night sky would be almost empty. No Andromeda, no nearby galaxies. Just a few faint smudges, impossibly distant. And the rest, darkness. Imagine being an astronomer in a galaxy located in a void. You'd look up and see almost nothing. A handful of stars in your own galaxy. Maybe one or two distant galaxies barely visible. You'd have no idea that the universe was filled with structure, with billions of galaxies arranged in webs and filaments. You'd think the universe was mostly empty, and you'd be wrong, but you'd have no way to know. This raises a question. How much of the universe's structure are we missing? How much is hidden beyond our ability to see beyond the edge of the observable universe, or obscured by cosmic dust, or invisible because it doesn't emit light? We map what we can, we measure what we can, but we're limited by distance, by technology, by the speed of light itself. The cosmic web teaches us something important about scale. When you're close to something, it looks solid. A galaxy looks like a dense cluster of stars. But zoom out, and it becomes a dot. Zoom out further, and dots become filaments. And filaments become a web. And the web becomes a texture, a pattern, a structure so large that even light takes hundreds of millions of years to cross it. At every scale, the universe reveals new layers of organization. And at every scale, we find ourselves smaller than we thought. Scientists have studied the cosmic web using a survey called the Sloan Digital Sky Survey. one of the most ambitious astronomical projects ever undertaken. Over the course of 2 decades, telescopes mapped the positions and distances of millions of galaxies, creating a 3-dimensional map of the nearby universe. And what they found was breathtaking. Not chaos, not randomness, but order. A delicate, intricate structure like lace woven from light. There's a simulation called the Millennium Run, conducted in 2005, that modeled the formation of the cosmic web from the Big Bang to the present day. It tracked over 10 billion dark matter particles, each representing a chunk of mass billions of times larger than the Sun, and let gravity shape them over 13.8 billion years of simulated time. The result was a universe that looked almost identical to the one we observe. Filaments, voids, clusters, superclusters, all emerging naturally from the laws of physics, from gravity acting on matter over cosmic time. But the Millennium Run also revealed something unsettling. Most of the universe's matter is in the filaments, not the clusters. The bright spots, the places where galaxies gather, the places we can see and study, represent only a small fraction of the total mass. The rest is hidden in the dark matter filaments, invisible, undetectable, except through its gravitational effects. We live in the bright spots, but most of the universe exists in the spaces between. Let's talk about motion. Because nothing in the universe is standing still. Galaxies aren't just sitting in the cosmic web. They're flowing along it, drifting, pulled by gravity. The Milky Way is moving at about 630 kilometers per second. Relative to the cosmic microwave background, the faint glow left over from the Big Bang. Part of that motion is due to the expansion of the universe. Part of it is due to the gravitational pull of nearby structures. And part of it is due to the flow along the cosmic web toward the Great Attractor, toward the Shapley supercluster, toward regions of higher density. This motion is called peculiar velocity, which is a misleading name. It sounds strange, but it just means motion that's not caused by the universe's expansion. It's the motion caused by gravity, by the pull of mass on mass, by the structure of the web itself. And measuring peculiar velocities has taught us something profound. The universe isn't just expanding uniformly, it's flowing. Galaxies are rivers, streams, currents moving through the cosmic web like water through a landscape. Laniakea. Our supercluster is defined not by proximity, but by flow. It's the region of space where galaxies are moving in the same general direction, pulled by the same gravitational basin. Beyond Laniakea's edge, galaxies flow in different directions toward different attractors. The boundary isn't a wall, it's a watershed, a divide between regions of space that are gravitationally distinct. And this raises a thought that might keep you awake or help you drift. We think of the Milky Way as our home, and it is. But the Milky Way is also just one node in a vast network, one intersection in a cosmic highway system. And we're moving, not wandering aimlessly, but flowing along invisible currents shaped by forces we can't see toward destinations we'll never reach in any human lifetime. The cosmic web is dynamic. It's not frozen, it's evolving. Filaments grow thicker as galaxies flow into them. Voids grow larger as matter drains out. Clusters merge, creating even larger clusters. And over trillions of years, as the universe continues to expand, the web will stretch. Filaments will thin. Clusters will become isolated islands separated by distances so vast that light from one cluster will never reach another. The universe will become lonelier, darker, quieter. But that's far in the future. Right now, the web is alive, flowing, connecting, and we're part of it. The matter in your body was once part of a filament, then a galaxy, then a star, then a planet. And someday it will return to the web, scattered by the death of the sun, drifted into interstellar space, pulled along dark matter currents, reformed into new structures. The web doesn't just hold the universe together, it recycles it. There's a beauty in that. a kind of cosmic circularity. Nothing is permanent. Everything is in motion. And the largest structures in the universe, the ones that seem eternal and unchanging, are actually flowing, shifting, evolving on time scales too long for us to perceive. Think about it this way. If you could watch the universe and fast forward billions of years, compressed into seconds, you'd see the cosmic web like a living thing. Filaments pulsing, clusters brightening and dimming as galaxies merge and scatter. Voids expanding like bubbles, the whole structure breathing, growing, changing, not static, not dead, but alive with motion, with gravity, with the slow dance of matter moving through space-time. And yet, from within the web, from our small corner of Laniakea, everything seems still. The stars don't move noticeably in a human lifetime. The galaxies hang in the sky fixed. The web itself is invisible, detectable only through careful measurement and mathematics. We live inside the largest structures in the universe and can't see them. Not directly, we have to infer, map, calculate, imagine. But now we've seen the web, we've mapped its shape, we've traced its filaments, and we know where we are. Not at the center, not at the edge, just somewhere in the middle. A small galaxy in a small group, in a modest supercluster, flowing through a web so vast, it makes even superclusters seem small. And still, there's farther to go. Because the cosmic web, immense as it is just the structure within the observable universe. Beyond that, there's more, much more. Regions of space we'll never see because their light hasn't had time to reach us yet. Because the universe is only 13.8 billion years old, and light can only travel so far in that time. And at the very edge of what we can observe, there's a horizon, a boundary. Not a wall, but a limit to knowledge itself. There's a structure in the universe so large it shouldn't exist. Not according to our theories, not according to the math. And yet, there it is, stretching across 10 billion light years of space, a wall of galaxies, a filament so immense that light takes 10 billion years just to travel from one end to the other. That's nearly 3/4 the age of the universe itself. It's called the Hercules Corona Borealis Great Wall, and it breaks the rules. In cosmology, there's a principle called the cosmological principle. It states that on large enough scales, the universe should be homogeneous and isotropic, uniform, the same in all directions. No matter where you look, no matter where you are, the universe should look roughly the same. Galaxies should be distributed evenly. Structures should be limited in size. There should be a maximum scale beyond which everything smooths out into uniformity. That maximum scale is thought to be about 1.2 billion light years. Beyond that, the universe should look smooth, featureless. But the Hercules Corona Borealis Great Wall is 10 billion light years across, 8 times larger than it should be, and its existence challenges everything we thought we knew about how the universe organizes itself. The structure was discovered in 2013 by a team of astronomers studying gamma-ray bursts, the most energetic explosions in the universe. Gamma-ray bursts happen when massive stars collapse into black holes, releasing more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. These bursts are visible across vast distances, making them useful as cosmic markers. By mapping the positions of gamma-ray bursts in three-dimensional space, astronomers can trace the distribution of galaxies. And when they did this, they noticed something strange. The bursts weren't evenly distributed, they clustered, and the cluster they formed was enormous. At first, researchers thought it might be a statistical fluke, random chance. But the signal was too strong, too persistent. The cluster stretched across 10 billion light years, contained thousands of galaxies, and had a density significantly higher than the surrounding space. It wasn't a fluke, it was real. A structure so vast, it redefined what we thought was possible. The discovery sent ripples through the cosmology community. Because if structures this large can exist, it means our models of the universe's formation are incomplete. Something is missing. Either dark matter behaves differently than we think, or there were larger than expected fluctuations in the early universe, or the cosmological principle, the idea that the universe is uniform on large scales, is wrong. And if it's wrong, then much of modern cosmology, which relies on that principle, needs to be reconsidered. But before we panic, let's understand what this structure actually is. It's not a solid wall. It's not a barrier you could touch or see. It's a statistical concentration of galaxies, a region of space where the density of matter is higher than average. If you could somehow stand in the middle of the Hercules Corona Borealis Great Wall, you wouldn't notice anything unusual. The galaxies would still be millions of light years apart. The sky would still look mostly empty. The wall only reveals itself when you map thousands of galaxies across billions of light years and plot their positions. Then the pattern emerges, a concentration. A thread in the cosmic web larger than any thread should be. Scientists suggest that structures like this formed from tiny quantum fluctuations in the fabric of the early universe. In the first fractions of a second after the Big Bang, space itself rippled with tiny variations in density. Some regions were slightly denser, some were slightly less dense. And over billions of years, those tiny differences grew. Gravity amplified them. The denser regions pulled in more matter, becoming even denser. The less dense regions emptied out, becoming voids. And slowly over cosmic time, the universe's structure emerged. Filaments, walls, clusters, superclusters. But here's the problem. The universe is only 13.8 billion years old. That's the amount of time gravity has had to work to grow structures from those initial fluctuations. And according to calculations, there hasn't been enough time for a structure 10 billion light years across to form. Gravity works slowly. It takes time for matter to clump, for filaments to connect, for walls to coalesce. A structure this large should take longer to form than the current age of the universe. And yet, it exists. Some astronomers have proposed alternative explanations. Maybe the structure isn't a single coherent wall. Maybe it's a projection effect, a chance alignment of several smaller structures that happen to look connected from our perspective. Like looking at a city skyline and mistaking separate buildings for a single long structure because they line up from your viewpoint. It's possible, but the statistical analysis suggests otherwise. The density of galaxies in this region is too high, too concentrated to be a random alignment. Others suggest that our understanding of the early universe needs to be revised. Maybe the initial fluctuations in density were larger than we thought. Maybe dark energy, the mysterious force causing the universe to expand at an accelerating rate, behaved differently in the early universe. Maybe there are aspects of cosmic evolution we haven't accounted for. Physics we don't yet understand. This is the edge of knowledge, the place where observations push against theory, where the universe surprises us, and where we're reminded that for all our telescopes, all our equations, all our models, the cosmos still has secrets. Let's step back and think about what it means to measure something 10 billion light years across. Light from the far edge of the Hercules Corona Borealis Great Wall has been traveling toward us for 10 billion years. It left when the universe was only 3.8 billion years old, less than a third its current age. The galaxies we're seeing aren't as they are now. They're as they were billions of years ago, young, forming stars, colliding, evolving. By now, in the present moment, those galaxies have aged. Some have merged, some have died, some have drifted apart, but we can't see any of that because the light showing us their current state won't arrive for another 10 billion years. This is the fundamental strangeness of astronomy. We don't see the universe as it is. We see it as it was. The farther we look, the deeper into the past we see. And at the scale of the Hercules Corona Borealis Great Wall, we're looking so far back that we're seeing the universe in its adolescence. Still growing, still chaotic, still figuring out its structure. There's a humbling lesson in that. We map the universe, we name its structures, we measure its scales. But we're always looking at ghosts, echoes of light from a past that no longer exists. The universe we observe is a memory, and the universe as it exists right now, this very moment, is unknowable, hidden behind the cosmic horizon, invisible. But let's talk about other large structures, because the Hercules Corona Borealis Great Wall isn't alone. There are other contenders for the title of largest structure in the universe. The Sloan Great Wall, discovered in 2003, stretches 1.37 billion light years. The giant GRB ring, identified in 2015, is about 5.6 billion light years across. The BOSS Great Wall, found in 2016, spans roughly 1 billion light years. Each discovery pushes the boundaries of what we thought possible. Each one forces us to reconsider our models. And then there are the supervoids, regions of space with far fewer galaxies than average. The KBC void, which some scientists suggest we might be living inside, is about 2 billion light years in diameter. The cold spot in the cosmic microwave background, a mysterious region where the temperature is slightly lower than average, might be caused by a supervoid nearly 1.8 billion light years across. These voids are as significant as the walls, because structure isn't just about where matter is, it's also about where matter isn't. The cosmic web is a balance, filaments and voids, walls and emptiness, high density and low density. And the largest structures, the ones that challenge our understanding, exist at the extremes. The densest concentrations, the emptiest voids, the places where the universe's texture becomes most pronounced. There's a thought experiment astronomers use to understand cosmic structure. Imagine the universe as a sponge. The solid parts are filaments and walls where galaxies cluster. The holes are voids where almost nothing exists. And the entire structure is expanding slowly, stretching, pulling the sponge apart. Over time, the filaments thin. The holes grow larger. The structure becomes more diffuse. Eventually, trillions of years from now, the sponge will be so stretched that the filaments break apart. Galaxies will become isolated, alone, drifting through voids so vast that no light from neighboring galaxies will ever reach them. But that's the distant future. Right now, the sponge is still intact, still holding together, and structures like the Hercules Corona Borealis Great Wall show us the sponge at its most extreme, the thickest filaments, the densest nodes, the places where the universe has concentrated its matter most dramatically. And here's what's beautiful about this. Every time we find a structure that shouldn't exist, every time we measure something larger than our theories predict, we learn. We refine our models. We ask better questions. We build better telescopes. We probe deeper. And the universe, patient and indifferent, reveals itself layer by layer, not because it wants to teach us, but because we refuse to stop looking. The Hercules Corona Borealis Great Wall is a reminder that the universe is stranger than we imagine, that our theories, elegant as they are approximations, maps not territories, and that the territory, the actual universe, is wilder, more complex, more surprising than any equation can fully capture. So, what does this mean for us? For humanity looking up from our small planet, trying to make sense of scales so vast they dwarf even our largest metaphors. It means we're still learning, still discovering, still at the beginning of understanding. The universe is 13.8 billion years old. Human civilization is about 10,000 years old. Modern astronomy is barely 400 years old. We've been looking at the cosmos with serious intent for less than a cosmic blink, and already we've found structures that challenge the limits of possibility. Imagine what we'll find next, as telescopes improve, as surveys map more galaxies, as simulations become more sophisticated. We might find structures even larger than the Hercules Corona Borealis Great Wall. Or we might discover that this structure is part of something even more immense, A hierarchy we haven't yet imagined, patterns within, patterns within, patterns extending beyond the edge of what we can observe. Or maybe the Great Wall is the largest structure there is. Maybe we've reached the upper limit. Maybe the cosmological principle holds after all, and this structure is an outlier, a rare statistical fluctuation, the universe testing the boundaries of its own rules. We don't know yet, and that's the thrill, the not knowing, the reaching, the endless asking of questions that don't have answers yet, but might someday. There's a quote often attributed to the physicist J.B.S. Haldane, though the exact wording varies. The universe is not only queerer than we suppose, but queerer than we can suppose. And the Hercules Corona Borealis Great Wall is proof of that. We built theories to explain the universe. We tested them. They worked mostly. And then we found something that didn't quite fit. And instead of ignoring it, we paid attention. We measured it. We tried to understand it. And in doing so, we pushed the boundaries of what we thought was possible. That's the story of science. Not certainty, not dogma, but curiosity, and the willingness to be wrong, to revise, to adapt, to follow the evidence even when it leads somewhere uncomfortable, even when it challenges the foundations of what we thought we knew. The universe doesn't owe us understanding. It doesn't simplify itself for our convenience. It is what it is, vast, complex, indifferent. And yet, we keep trying to understand it. We keep mapping, measuring, wondering. And every so often we find something that takes our breath away. A structure so large, so improbable, so beautiful, that it reminds us why we look up in the first place. Not to conquer, not to own, but to see, to know, to be part of something larger than ourselves. Even if that something is 10 billion light years wide and challenges everything we thought was true. And now, after touching the largest single structure ever found, we turn to the largest thing of all. Not a wall, not a filament, not a cluster, but the entirety. The observable universe itself. The sphere of everything we can see, everything we can know, everything that light has had time to show us in 13.8 billion years. A boundary not of space, but of time and knowledge. There's an edge to everything we can know. Not a wall, not a boundary you could touch, but a horizon. A limit imposed not by space, but by time, by the speed of light, by the age of the universe itself. Beyond this horizon, there is more, much more. Galaxies, stars, worlds we will never see. Not because they don't exist, but because their light hasn't had time to reach us, and never will. This is the observable universe, a sphere 93 billion light years in diameter, centered on Earth. Everything we can see, everything we can measure, everything we can know, and beyond it, silence, mystery, the unknowable. The observable universe contains an estimated 2 trillion galaxies, each one holding hundreds of billions of stars, each star potentially hosting planets, moons, worlds. The numbers become meaningless after a while. 2 trillion galaxies. That's more galaxies than there are stars in the Milky Way. More galaxies than grains of sand on all the beaches of Earth. And that's just what we can see. The actual universe, the whole universe, might be infinitely larger. We don't know. We can't know. The horizon hides it from us. Here's the paradox. The universe is 13.8 billion years old. Light travels at a finite speed, about 300,000 kilometers per second. So, you might think the observable universe should be 13.8 billion light years in radius, but it's not. It's 46.5 billion light years in radius. Why? Because the universe has been expanding the entire time. The light we see from the most distant galaxies began its journey 13.8 billion years ago, when those galaxies were much closer to us. But in the time it took for that light to reach us, space itself expanded, carrying those galaxies farther away. So now, they're 46.5 billion light years distant, and the light we're seeing is ancient. A message from a time when the universe was young, hot, and strange. The farthest thing we can see is not a galaxy. It's the cosmic microwave background, or CMB, a faint glow of radiation filling all of space left over from the Big Bang. About 380,000 years after the universe began, space cooled enough for atoms to form. Before that, the universe was a hot, dense plasma of particles and light, opaque to radiation. But when atoms formed, light could finally travel freely. That light has been traveling ever since, stretched and redshifted by the universe's expansion until now it appears as microwave radiation. Faint, cold, uniform. But there, the CMB is a photograph of the infant universe, a snapshot of what space looked like when it was only 380,000 years old. And embedded in that glow are tiny fluctuations, tiny variations in temperature less than 1 part in 100,000. Those fluctuations are the seeds of everything, the slight differences in density that eventually grew into galaxies, clusters, superclusters. The cosmic web. Everything we've talked about tonight began as tiny ripples in the CMB. In the 1960s, 2 scientists named Arno Penzias and Robert Wilson were working at Bell Labs testing a sensitive radio antenna. They kept detecting a persistent hiss, a background noise they couldn't eliminate. They thought it was interference, maybe pigeons nesting in the antenna. They cleaned it. The noise persisted. Eventually, they realized what they were hearing: the echo of the Big Bang, the cosmic microwave background. They won the Nobel Prize for the discovery in 1978, not for finding something new, but for recognizing what they'd stumbled upon: the oldest light in the universe, the afterglow of creation. Satellites like COBIT-WMAP and Planck have mapped the CMB in exquisite detail, measuring those tiny temperature fluctuations across the entire sky. And from those measurements, we've learned the age of the universe, its composition, its geometry, its fate. The CMB is the most important scientific discovery of the 20th century, a Rosetta Stone for cosmology, and it marks the edge of what we can see. Beyond it, there's nothing. Not because nothing exists, but because light from earlier times hasn't escaped. The universe before 380,000 years was opaque, a wall of light and energy we can't see through. But scientists are trying, not with light, but with gravitational waves, ripples in space-time caused by violent cosmic events. Gravitational waves aren't blocked by matter the way light is. They pass through everything. And if we could detect gravitational waves from the Big Bang itself, we could see farther back, to the first fractions of a second, to moments so early that time itself becomes strange and uncertain. Experiments are being designed, detectors are being built, but we're not there yet. For now, the CMB is the edge. Let's talk about what the observable universe actually contains. 2 trillion galaxies, yes. But what else dark matter? About 27% of the universe's total mass energy. We can't see it, can't touch it, can't detect it directly. But we know it's there because of its gravitational effects. Without dark matter, galaxies would fly apart, clusters wouldn't hold together, the cosmic web wouldn't exist. Dark matter is the glue holding the universe together, and we still don't know what it is. Particles, fields, something else entirely. It's one of the great unsolved mysteries of physics. Then there's dark energy, about 68% of the universe's total mass energy, even stranger than dark matter. Dark energy is causing the universe's expansion to accelerate. Galaxies aren't just moving apart. They're moving apart faster and faster. Discovered in 1998 by 2 teams studying distant supernovae, dark energy was a shock. Most cosmologists expected the universe's expansion to be slowing down, pulled back by gravity. Instead, it's speeding up, pushed by something we don't understand. Dark energy permeates all of space, exerting a kind of negative pressure driving expansion. And we have no idea what it is. a property of space itself, a field. A cosmological constant, as Einstein once proposed and later abandoned. No one knows. So here's the tally. Everything we can see, all the stars, planets, gas, dust light accounts for only about 5% of the universe's total mass energy. The other 95% is dark, invisible, unknown. We live in a universe where most of what exists is hidden from us. And that's humbling. We've mapped galaxies, measured distances, traced the cosmic web, but we've only scratched the surface. The universe is mostly mystery. And then there's the question of what lies beyond the observable universe. Because the observable universe is just the part we can see, the part where light has had time to reach us. But space doesn't end there. It keeps going. How far, we don't know. Maybe forever. Some models suggest the universe is infinite, that beyond our horizon there are infinite galaxies, infinite stars, infinite worlds. Everything that can happen does happen somewhere out there. Other Earths, other versions of you, living different lives, making different choices. An infinity of possibilities, all real, all existing, but forever beyond our reach. Other models suggest the universe is finite but unbounded, like the surface of a sphere. You could travel in a straight line forever and never reach an edge, but you'd eventually come back to where you started. Space curves back on itself. It's hard to visualize, hard to comprehend, but mathematically, it's possible. And we don't yet know which model is correct. The universe might be infinite, or it might loop, or it might have some other geometry we haven't imagined. The data isn't precise enough to tell. There's also the possibility of a multiverse, not just multiple regions of one universe, but entirely separate universes, each with different physical laws, different constants, different histories. Some versions of inflationary theory, which describes the rapid expansion of the early universe, suggest that inflation didn't happen once, but is happening constantly, creating bubble universes, each one a separate cosmos. Our observable universe would just be one bubble in an infinite froth, and we'd have no way to detect the others, no way to visit them, no way to know if they exist. It's a beautiful idea, a troubling idea, because if true, it means most of reality is permanently out of reach. But let's come back to what we can observe, what we can measure. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies, and every photon of light we see, every piece of data we collect, is a message from the past. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. When you look at the CMB, you're seeing the universe as it was 13.8 billion years ago. Astronomy is archaeology. We dig not through dirt, but through time. Every observation is a glimpse into history. And the farther we look, the deeper we see. The James Webb Space Telescope, launched in 2021, is designed to look farther than ever before, to see the first galaxies that formed after the Big Bang, galaxies that existed when the universe was only a few 100 million years old, small, chaotic, still forming. These galaxies are so distant, so redshifted, that their visible light has been stretched into the infrared, and Webb, with its massive mirror and infrared sensors, can see them. Early results are already rewriting textbooks. Galaxies that shouldn't exist yet according to old models. Galaxies that are larger, brighter, more structured than expected. The universe once again surprising us. And here's the thing. Every time we build a better telescope, every time we look deeper, we find things we didn't expect. Structures that challenge our theories. Phenomena that force us to revise our understanding. The universe doesn't conform to our expectations. It is what it is. Wild, strange, indifferent. And all we can do is keep looking, keep measuring, keep wondering. There's a concept in cosmology called the particle horizon. It's the boundary of the observable universe, the farthest distance from which light has had time to reach us. But the particle horizon is growing, not because the universe is getting older, though it is, but because light from farther regions is constantly arriving. Every second, the observable universe expands slightly, not because space is expanding faster, but because light from previously unreachable places finally reaches us. In 1 billion years, if humanity still exists, if we're still looking up, we'll be able to see galaxies that are invisible to us now. The horizon will have moved, and what we can know will have grown. But there's also a dark side to this. Because the universe's expansion is accelerating, driven by dark energy, distant galaxies are moving away from us faster than light can catch up. There are galaxies we can see now whose light will never reach us again in the future. As time goes on, they'll slip beyond the horizon, disappear, become unreachable. Not because they're destroyed, but because space itself is pulling them away faster than light can bridge the gap. In trillions of years, if the acceleration continues, the observable universe will shrink. Galaxies will fade, clusters will disappear, and eventually all that will be visible is our local group. The Milky Way and Andromeda merged into Milkomeda, drifting alone in a dark, empty sky. An island in an ocean of void, isolated, forgotten. That's the far future. A future so distant, it's almost meaningless. But it's a reminder that observation has limits, that knowledge has boundaries, that there are things we will never know, not because we lack the tools, but because the universe itself hides them from us. And yet, right now in this moment, we can see 2 trillion galaxies. We can trace the cosmic web. We can measure the CMB. We can calculate the age size and composition of the observable universe. We know more about the cosmos than any generation before us. And we're still learning, still discovering, still reaching. Carl Sagan once said, "We are a way for the cosmos to know itself." And it's true. We are made of atoms forged in stars. We are animated stardust, walking on a planet made of the remnants of ancient supernovae. And we have the capacity, the curiosity, the audacity to look up and ask, what is all this? Where did it come from? Where is it going? Those questions might not have final answers, but the asking, the searching, the wondering, that's what makes us human. The observable universe is the largest thing we have ever seen, but it's not the largest thing that exists. It's just the largest thing we can see. The horizon of our knowledge, and beyond it more, always more. Galaxies will never visit, stars will never name, worlds will never know. And that's okay, because what we can see, what we have seen, is already more than enough to fill a lifetime with awe. We've drifted through distances tonight that collapse the imagination. From the moon just 384,000 kilometers away to the edge of the observable universe 93 billion light years across. From the familiar to the incomprehensible. And at every step, we've learned the same lesson, that we are small. And that smallness, rather than diminishing us, connects us to the stars, to the galaxies, to the web of everything. We are part of it, not separate, not alone, just one small thread in a tapestry so vast, it takes light billions of years to cross. Maybe knowledge was never meant to be complete. Maybe the horizon, the boundary between the known and the unknown, is a gift, a reminder that there's always more to discover. That curiosity never runs out of questions. That wonder never runs dry. Sleep well. Dream gently. And when you wake, remember. You are here in a universe 93 billion light years wide, on a small planet orbiting an average star in a quiet corner of a spiral galaxy, drifting through a web of light and dark matter surrounded by mystery. And somehow, impossibly, you are aware of it. You can see it. You can think about it. You can feel the weight of it, settling softly like snow on a winter night. Good night.